Hey everyone. So for this session, we're going to talk about both solar and lunar eclipses. So an eclipse occurs basically whenever one celestial object passes into the shadow of another celestial object, or one celestial object passes in front of or behind of some other object. So there's two main kinds of eclipses that we generally talk about, just in everyday discussions when we talk about, things in astronomy. One is the lunar eclipse, where the moon passes into the shadow of the Earth. We've got the sun, we've got the Earth, and the moon orbiting around the Earth. Sometimes the moon will pass into that shadow, and that's when we get what's called a lunar eclipse. The other one, the solar eclipse, is where the moon casts a shadow onto the Earth. So we've got the moon orbiting around the Earth. Sometimes the moon will pass in front of the sun and cast a little bit of its shadow onto the Earth. Now, there can be cases where if the moon is, say, over here, only part of the moon isn't completely in Earth's shadow. It can still see a little bit of the sun, or other points on the Earth where if you're right at this point on the Earth right here, the moon would completely block your view of the sun, or in other locations, you'd get what's called a partial eclipse, where the moon is just blocking a little bit of the sun. So let's start with just a little simulation of these two general kinds of eclipses. And as we're going through this, I've got this comparison of solar and lunar eclipses. I recommend kind of building up the different parts of this just for the kind of quick fact sheet about solar and lunar eclipses. So feel free to follow along with that to use as a study tool. So this is a little simulation about eclipses, and you can say, here's the sun, here's the Earth, and the moon orbiting around the Earth. Notice this is definitely not to scale, but the moon is going to be casting a shadow, and at some locations on the Earth, you might have what's called a partial solar eclipse. The moon is blocking part of the sun's light, but there is also still some sunlight that can reach the person. The moon is just blocking some of that light in these cases. But if the moon's at the right location, well, now this person on the Earth, their view of the sun is completely blocked off by the moon. This would be an example of a solar eclipse. Okay. On the other side of the orbit, when the moon's on the far side of its orbit, well, here's the shadow that the Earth is casting. This would be a partial shadow. You can still see a little bit of the sun from this side and this side. This would be the darkest part of the shadow. So we can have a case where we've got a partial lunar eclipse. So part of that light is being blocked. Now it's completely in the Earth's shadow, and all of that light from the sun is being blocked by the Earth. So again, this can help you identify some of the differences between solar and lunar eclipses, but we're going to go into more detail on the similarities and differences between these kinds of eclipses. So let's start with solar eclipses. This is basically when the moon passes in front of the sun and casts a shadow on the Earth. So from our viewpoint, the moon blocks our view of the sun for a few minutes. So for a total solar eclipse, these don't last very long. The duration is only a few minutes for totality. And let's think, what phase, if we have this solar eclipse, if the moon is on the same side of the Earth as the sun is, what phase would the moon be in, like just before and just after having this eclipse happen? So as always, pause the video, try to answer that. What phase would we see for the phase of the moon during a solar eclipse? Well, if the moon is on this side, we can't see any of the visible side of the moon being illuminated by light, so that would be the new moon phase. So this is actually a photo of the moon's shadow moving across the Earth This is over Turkey, taken from the Mir space station in 1999. You can actually see the shadow that the moon is casting on the Earth. From our viewpoint, the sun would look like this, where the moon is blocking our view of the sun, and you just see the outer kind of atmosphere of the sun, the corona of the sun, that's usually invisible. Never try to look directly at the sun without proper safety equipment. This is images taken by a satellite during an eclipse, and along the bottom, hopefully the recording is picking this up decently, you can see the shadow of the moon kind of make this cut across, that would be the southern part of Africa and the Indian Ocean. So again, these solar eclipses are when the moon is casting a shadow onto the Earth. So the appearance of this would be the moon blocks our view of the sun. So moon blocks view of sun. Now, there's a little bit of an interesting, this one actually is kind of a coincidence of how large the moon appears on the sky compared to how large the sun appears on the sky from the Earth's location. Because it turns out that the sun and the moon have a very similar angular size. What we mean by angular size is how much do you have to kind of turn your head to look from one side of an object to another? What's the angle? What's the angle across the sky that that object extends? Okay. Now, this can be affected by a couple of things. If I have an object that has a certain physical size, but it's pretty close to you. Let's see if I can hold this a little bit closer. If I have an object and it's close to you, it has a large angular size. Okay? It's taking up a lot of the screen right now. If I move it back, its physical size is exactly the same, but how far you have to move your head to look from one side of it to the other is not nearly as large. So if I have an object of the same angular size, but it's further, the same physical size, but it's further away, its angular size will be smaller. It will appear smaller to my eye. Now, by kind of an interesting coincidence, if we compare the Earth and the moon, the sun and the sun is much larger than the moon. However, the sun is also a lot further away than the moon is. So let's say that this is the moon and this is the sun. This is still not to scale, even though this one's bigger. But if the sun is further away and the moon is closer, they can actually have the same angular size, even though their physical sizes are significantly different. Okay. The moon, here, let me stop my share for a second so you can hopefully see that a little bit clearer. So again, let me try that demonstration again. Again, the moon is a lot smaller than the sun, but if the moon is also a lot closer, if it's the right pattern, then they can be the same angular size on the sky. So the moon can just barely block the sun. The moon also does get a little bit closer to us, more likely to block out the sun, and sometimes a little bit further away, less likely to block out the entire sun. Maybe we get a little kind of halo thing happening around that. The sun also does get a little bit larger and a little bit smaller, since sometimes the Earth is a little bit closer or a little bit further away from the sun, but that's a significantly smaller extent than the moon does this. But again, by a kind of surprising coincidence, the moon and the sun have pretty close to the same angular size in the sky. The sun is about 400 times the size of the moon, 400 times the diameter of the moon, but it's also about 400 times further away than the Earth is. So due to this effect, there's a couple of different kinds of eclipses that we can have. A total eclipse, where the moon completely blocks our view of the sun. So let's say this is the sun, moon's coming in, it completely blocks our view of that. Okay? That would be an example of a total eclipse. However, if the moon is a little bit further away in its orbit, we might get what's called an annular eclipse, where there's a little bit of the outer edge of the sun that you can kind of see. This would be an example of an annular solar eclipse. And this, again, occurs when the moon is further from us. If the moon is further away from us, it looks smaller on the sky, so you can see more of the sun. We also have a partial solar eclipse, where maybe you're not right on the path of totality. If you remember the last large eclipse to go through the United States, then if you weren't right on the path of totality, you might have seen something that looks like this. Instead of the moon passing directly in front of the sun, it might have passed a little bit below or a little bit over top. So if it passes a little bit too low, it'll block out part of the sun for a while, but you'll still be able to see at least part of the sun the entire time. That would be a partial solar eclipse. This is a map of where the 2017 eclipse passed across the continental United States. So the large dark area, that's where you would have seen a partial solar eclipse. That little black dot in the middle, that's where you would have seen the total solar eclipse. And again, you would only see that total solar eclipse for a couple of minutes. Another kind of thing to point out here is that these models and calculations were done in 2000. So these predictions are based on our understanding of gravity and of orbits and where the moon is going to be at different times of the year, at different times of over the course of many, many years. And you can actually go to the NASA website where they have, for the next few thousand years, a list of where all the eclipses are going to be, where they're going to be viewable from. Again, when we're developing scientific models, we want to make testable models of nature that can make predictions. And at least this one matched up exactly as was expected. These are the projected paths of the different annular and solar eclipses from 2001 to 2020. So again, this one's a little bit old. These are the total solar eclipse paths for 2001 to 2050. A couple of things about these paths. You'll notice that most of these are only visible. You'll only get those total solar eclipses across relatively narrow strips across the Earth. So this approximate area of the Earth where the eclipse can be seen, for the solar eclipse, it's just narrow strips across the Earth's surface. So narrow strips across Earth. Earth's surface. And notice these are not around very often. For 2001 to 2050, there was one in 2017, one in 2024, one in 2008, 2033, 2044, 2045. So the frequency that you get to see it, partly due to the fact that you can only see it across a narrow band, is, only a few times per, like maybe every 5 to 10 years or so. So the frequency of eclipse, 5 to 10 years due to only being viewable from a small area. So only viewable from small area. And again, the eclipses only last a few minutes each time. And as we already talked about, the moon would be in the new moon phase during these solar eclipses. We've got a similar thing for annular solar eclipses. Again, this is kind of listing some of them out. So all in, yeah, it looks like every 5 to 10 years, and somewhere in the continental US, there will be some kind of solar eclipse. And again, for this one, is the moon further or closer to the Earth during one of these annular eclipses? Notice the moon is looking a little bit smaller on the sky. So if it appears to be smaller on the sky, does that imply that it's closer to us or further away from us? So that one would be further away from us. And again, the eclipse geometry, since we didn't put that one in, let's finish that one up now. We've got the sun, we've got the moon, and we've got the Earth. And again, in that case, the moon is casting a shadow onto a little bit of the Earth. Okay. So the next one is lunar eclipses. The moon passes into the shadow of the Earth. So in this configuration, the moon is on the far side of the Earth, away from the sun. So the visible side of the moon is the side that's illuminated. So what phase of the moon would it be in just before and just after going through this portion of the shadow? Yeah, that would be the full moon phase. So again, there's parts where the moon might just be in part of the Earth's shadow. When it gets into the darkest part of the shadow, you'll see the color of the moon actually change to red. And let me just go on a bit of a tangent as to why the moon gets this red hue to it. All around the edge of the Earth, there are sunsets going on. The sun is right near or just a little bit below the horizon, and you have these sunsets kind of circling around the edge of the Earth. For reasons that I'm not going to go into too much detail on right now, the red light from the sun makes it through more of the atmosphere and illuminates more of the atmosphere further on. This is why sunsets tend to have those kind of reddish colors. And all of those sunsets, some of that light is able to filter through, bounce through the atmosphere and make it through. And some of that red light is actually able to make it to the surface of the moon. That's what gives it that red color during a lunar eclipse. It's literally being lit up by all of the sunsets on Earth simultaneously. So again, when the moon passes into the darkest part of the Earth's shadow, that's when we get one of these lunar eclipses. And again, the moon will be full during those lunar eclipses. You can actually map out what is the shape of Earth's shadow in space. So this is kind of a sequence of images taking of the moon kind of superimposed over each other. And these kind of images are rather difficult to take because we're on a moving platform with the Earth rotating as well. So getting everything lined up correctly is a little bit difficult. But you can actually see the shape of the Earth's shadow. And whenever we measure this, it's always a circular shadow. And the only shape that casts a circular shadow, no matter what orientation it's in, is a sphere. Going back to, yeah, the Earth is definitely a sphere. And again, we can map out, well, when is the moon passing into the partial shadow, the penumbra? When is the Earth entering the umbra, the darkest part of the shadow? And we can measure this to high accuracy. Again, the geometry for this, let's go back to our page here and draw out this geometry. So we've got that is a horrible yellow. Let's see if I can make that a little bit better. We've got the sun. We've got the Earth. And over here we have the moon. And the moon is falling into the shadow of the Earth. For the solar eclipse, that total solar eclipse was only viewable from a narrow band across the Earth because the Earth's shadow on the moon isn't very large. However, when the moon passes into the Earth's shadow, basically about half of the Earth can see it. And the Earth is a lot bigger than the moon. So the moon is going to be in Earth's shadow for usually a couple of hours. So a couple of pieces of information on here. Since the Earth's shadow is really big, larger than the moon itself, usually totality lasts a couple hours. The appearance is that we see the illuminated part of the moon not being illuminated anymore. So moon stops being illuminated. Illuminated when in shadow. When in Earth shadow. And, well, basically, if you're on any part of the Earth that can see the moon during those hours, which is about half of the Earth, you're going to be able to see that lunar eclipse. So about half the Earth. And these happen usually around twice a year. So around 2 times per year. Now, a couple of things about the frequency. How often do we see these eclipses happen, solar and lunar eclipses? From most of the pictures that we've looked at, like if you look at this particular picture and say, well, as the moon orbits around the Earth, when the moon's on the far side, we get a lunar eclipse. When the moon's on the near side, we get a solar eclipse. So why don't we get an eclipse each time we have a new moon, each time we have a full moon? That is kind of where this two-dimensional picture fails a little bit. Okay? If we were doing a little bit better with a 3D picture, which I'm not good enough to draw, we would say, let's say we've got the Earth at the very center. So this is going to represent the Earth. And this frisbee, the surface of this, the edge of this frisbee represents the moon's orbit. Okay? And we're going to say that you're at the location of the sun. So if the moon's orbit was in line with the sun, then every time the moon went over here, we'd get a solar eclipse. Every time the moon went behind the Earth, we'd get a lunar eclipse. But that's not how the moon's orbit is quite oriented. It's actually tilted a little bit. So what we get is with this tilt, most of the time, the moon will pass a little bit too low or a little bit too high in order for one of those objects to pass into the shadow of the other. Okay? But as this kind of plate of the moon's orbit goes around the sun, it's kind of hard with the camera, but basically that path will change and eventually it'll be tilted something like this. And now, in these two configurations, if the moon happens to be passing through the ecliptic plane, the same plane as the orbit that the Earth takes around the sun, then it's much more likely that the moon will actually pass directly in front of the Earth or pass directly behind the Earth if we have it set up in this particular way. But then the moon will continue to orbit. Now we're back in, say, this kind of orientation, not likely to happen. It'll pass below or above. So these favorable conditions, these two periods where it's more likely that you're going to get an eclipse, this happens approximately every 6 months. And during these two times of the year, we'll usually get one solar eclipse and one lunar eclipse approximately 2 weeks apart. Again, the lunar eclipse can be viewable by about half of the Earth. So you're got pretty good odds on being able to see the lunar eclipse. The solar eclipse can only be seen across a narrow slice across the Earth, so it's much less likely that you're actually going to be in the right location on the Earth to be able to see one of those solar eclipses. So again, we have these eclipse seasons approximately every 6 months apart. It's not quite exactly 6 months apart because the plane that the moon is orbiting in is doing this kind of additional wobble that adds complication. But this is when it's more likely that you're going to get one of those, again, one solar eclipse and one lunar eclipse. So again, filling out the rest of this table is probably going to be helpful. Again, noticing those eclipse season patterns and why we don't get a solar and lunar eclipse every single time the moon orbits around the Earth. Just to end this off, I wanted to mention a couple of eclipses on other planets, because eclipses actually show up in a lot of other contexts as well. This is an image taken by a satellite that was going around Mars called the Mars Global Surveyor of one of Mars's moons, Phobos, that shadow being cast onto the surface of Mars. So these eclipses can happen on other planets as well. This is an image of the planet Venus passing across the face of the sun. These transits of Venus historically were very, very important in allowing scientists to first get accurate measurements of how large is the solar system. We're not going to go into too much detail for this course, but if you observe one of these transits of Venus from locations across the globe, if you get careful timing measurements of when the planet Venus starts to pass in front of the sun and when it passes by, you can actually measure how fast is Venus moving. And if you know the orbital period and how fast Venus is moving, you can start to actually measure how large is the solar system. This was first done, I think, in the 1700s. And here's the problem with trying to measure this. This transit of Venus, it'll happen twice, 8 years apart, and then you have to wait something like a little over 100 years for the next two transits of Venus to happen. So in the 1700s, when astronomers were first trying to make this measurement to figure out, well, how large is our solar system, this was in the time of, ships traveling, like wooden ships traveling to very distant areas. A number of European countries sent scientists and astronomers on missions to make these observations at different locations around the world. Also map out coastlines and, make treaties and encourage trade and, all those other benefits as well. But some of these voyages were absolutely miserable. This was the time of scurvy and, diseases and lots of problems. I can't remember the name of the scientist, but one of them went on one of these expeditions to try to measure this transit of Venus. Unfortunately, they were held up by weather and missed the first transit, so had to wait 8 years in order to see the next transit. I forget exactly where they were, but a lot of his crew got malaria. Waited 8 years for the next transit to happen. Day of the transit, overcast weather. So he wasn't able to make the measurements, eventually got the remainder of his crew that survived back home. And by the time he got back home, his family had assumed that he was dead and sold all his stuff. So, but luckily others were able to make the successful measurements and actually give us our first accurate estimates as to how large the solar system is. One last case of eclipses is in regards to a method we have for detecting planets outside of our own solar system. So if I have a star that's very, very far away, and there's a planet orbiting around it, very often the light from the star is so bright and the reflected light from the planet is so dim that you can't actually image the planet on its own. However, you can very, very accurately measure the brightness of that star. So if there's a planet orbiting around it, and it's in the right orientation, that planet might pass in front of its host star and block a little bit of the light, kind of like how we see Venus passing in front of the sun. And sophisticated instruments can measure, well, how much of the light is blocked. So this is the light from a star, and some of that light gets blocked as the planet passes in front of it. This is like 0.04% of the light being blocked. So 4 parts in 10,000. You need very, very accurate measurements for this. And if we see that dip in brightness happening regularly, well, we can measure we can identify that a planet's there. We can measure its orbital period. Depending on how much light is blocked, we can measure how large the planet is compared to its host star. This is one of the ways that we have for detecting exoplanets. So even though we generally talk about eclipses in terms of solar and lunar eclipses on the Earth, there are a bunch of other ways that eclipses are used in astronomy to study different kinds of physical systems. So we'll call that good for now. Have a good rest of your day.